Hello everyone. If you remember from my previous video where I showed you how to perform inverse kinematics in Coppelia sim, let me show you. So that's this video here. This is this model. You remember that in this Coppelia sim video, I used two different methods for inverse kinematics. One of them was pseudo-inverse, the other one was damped least squares. And this one was more stable, less accurate. This one is faster, more accurate, but it's sensitive to being close to singularity. So I want to explain these two methods. This one you probably know, that is very common and used. This one I just wanted to explain it a little bit further. Let's talk about these two methods. So first we go to the inverse kinematics, just briefly, very fast. Remember that the workspace velocities x dot, if x is the pose, in my notations I use xi for it in my robotics playlist, is related to the basically joint space velocities theta dot by this matrix Jacobian, which is not a fixed matrix. It does depend on the angles. Now, the inverse kinematics is where I give you the end effector pose x, which involves the xyz position as well as the three angles, let's say Euler angles or any other absolute angle presentation of the end effector frame in base. And I say this is, in general, this is a nonlinear function of the angles, right? Or the joint variables. You might instead, in my notations, I use q's typically instead of thetas because not all of the joints are necessarily revolute. Some of them are prismatic. So I say, I give you this end effector position. You give me the corresponding joint values, which give you that end effector pose. Okay. And since these are a bunch of nonlinear equations, right? So I need to solve them typically by a numerical solver. For specific scenarios, there are analytic solutions, but most of the time you have to use numerical solutions. And one of the problems that exists is sometimes this J matrix is not a square matrix, right? Because your robot is, let's say, redundant. In this example that I showed you in Coppelia sim, the robot is 7 DOF. So in that case, this is a 7 by 1, and this guy is a 6 by 1. So your Jacobian is a 6 by 7. So you cannot simply invert J, multiply it by x dot, and get theta dot, right? And then you might say, well, I want theta, I don't want theta dot, right? The inverse kinematics should give me the angles, not the angular velocity. So why even do I use this in the first place? Because this gives me theta dot. You're right, but if you're starting from some initial theta 0, and you know the theta dot that you need to reach to this specific end effector velocity at the moment, once you change your theta by this theta dot at every moment and keep moving until ultimately the x that you get from your forward kinematics equation reaches what? Reaches the x desired, or the error in the pose, which is the difference between them, goes to 0, then you can basically use the theta dot that you got from here and keep updating theta in an iterative manner. And I explained that in one of my previous videos, okay? So the problem, as I said here, is this J does not have an inverse. So what would you do in that case? Let's say when the system, the robot is redundant, then you use a pseudo-inverse of J. And pseudo-inverse is defined as here. This is basically the right pseudo-inverse. It is defined as J transpose times JJ transpose inverse. Because if this J plus, if you multiply J from the right side to it, the result is the identity matrix, and you can check that. So this will give you a solution. Now, which solution? Because we know when the robot is redundant, you have infinitely many solutions. So this one, this method that is called pseudo-inverse or undamped method, this only gives you one out of infinitely many solutions. Which one is this? This is what we call the minimum norm solution. So this one is trying to what? Minimize the norm of final theta such that still the end effector pose is equal to the forward kinematics applied to this theta. Okay, so it does solve this, but also minimizes the joint movements. And this is a really good, nice method. The good thing about it, it's simple, it's fast, and it is accurate. It gives you minimum joint motion. The only limitation it does have is the robot pose should be away from the singularity. In other words, that manipulability measure, right, which is how close you are to the singularities, should be a big number. If you're close, or a small number, sorry. If you're close to singularities, this method starts to go crazy. And you might say, why is that? Well, let me tell you why. So let's assume that you do a singular value decomposition on the J matrix, the Jacobian. So you get U sigma V, okay? Yes? Now what? Now the pseudo-inverse of J is going to be V sigma pseudo-inverse U, okay? Where sigma inverse is basically you're inverting the non-zero singular values in the sigma matrix. So this matrix and this matrix, sigma and sigma inverse, are related. This just their singular values are reciprocal of each other. Because remember, this matrix is a matrix of, it's a rectangular matrix of the singular value. So this is like sigma 1, sigma 2, let's say all the way to sigma n. And you can have a bunch of zeros here or a bunch of zeros here, depending on the dimension. So this one, what it does, the singular values of that are reciprocal of this guy. And what's the problem? The problem is when you get close to singularities, the singular values of sigma matrix go to 0. So the ones for the J pseudo-inverse or the sigma pseudo-inverse, guess what? They go to infinity. And that is where you start getting big joint velocities when you solve from here. When you solve for theta dots, the result that you get out of here, they are going to be very large. And so your update equations are not going to converge. So you start to be unstable near singularities. And if they are not really reachable or close to non-reachable points, your algorithm could easily go unstable and diverge. Okay, so that is the problem with this method. And I mentioned that once you have your theta dots, you can get theta and so on. You use an iterative method. Let me just explain that briefly here. And then we're going to talk about the second method. So let me tell you how exactly you solve the inverse kinematics iteratively. So let's say the solution that you want to have is F. Here, F is your forward kinematics equations, theta are your angles, and X target is the target pose of the end effector that you want to reach. So I gave you this X of target. You know the F functions. You need to find thetas, correct? That's your inverse kinematics problem. Now, most of the time, as I said, these are a bunch of nonlinear equations that you cannot necessarily solve so easily. So one of the things you can do is this. You are going to linearize them around the current configuration. How? You say X minus X target minus F at the current iteration. You approximate it by J times delta theta. Okay, and you might say, well, where did you get this one from? Okay, let me show you where I got that one from. So remember your velocity equations where X dot equals basically J times theta dot, correct? So if assuming that the steps that you're taking and the time steps are small, I can approximate this by, I say this is approximated by delta X is approximated by J times delta theta. And this is exactly your delta X. This is the desired X. This is the current X that you have. This is the current X. And this is J times delta theta. Okay, so this is the linearized version or approximate version of that. Fine. Now, if you have this, what would you do? You're going to solve for delta theta. How? You multiply both sides by pseudo-inverse of J. So that becomes identity, pseudo-inverse multiplied by this delta X. And that is going to be the change in the angle that you need at the moment. And once you have the change in the angle, now you multiply that by a learning factor, right? Again, add it to the previous theta and you get the new theta, and you keep updating based on this until the norm of the pose error becomes less than some epsilon or something. Then you would stop. So when I said iterative, this is how you do iterative, okay? And this is how you use the pseudo-inverse. So this is the pseudo-inverse iterative method. That's why in the Coppelia sim, you had to provide an iteration number, right? Let me show you here. When you created this ARM group, look here, basically inverse kinematics group, look, you gave it 10 maximum number of iterations, right? So because you don't want to stay in an infinite loop, so you give it the max iteration. If that doesn't converge in those many iterations, you get out. And look, this method had no damping. What is damping? I'll show you in a second. Let's talk about the damped least squares method. So what are you doing here? So here, instead of let's say this lambda, which is exactly your damping factor, let's say this lambda is 0. If this is 0, you see it's exactly the formula of pseudo-inverse, right? By the way, this is not a 1, this is the identity matrix, okay? So that is your identity matrix. So you're adding some small entity of identity matrix, a multiplier of that, to the pseudo-inverse, to this JJ transpose, then inverted and multiplied by J. The good thing is, once you do that, this matrix will never have 0 eigenvalues and or infinite eigenvalues, and it will always have some results. Okay, and you might say, well, it has, but remember that this is not going to give you the perfect solution because you are really adding something here, right? So the result of this is not supposed to be as accurate as the pseudo-inverse, because that exactly gives you the relation. This one you're kind of manipulating, adding something in so that this pseudo-inverse always exists, but at the price of a little bit less accuracy. You're right, that's correct. And that is exactly what we want. When we are getting close to singularity, we want this method to still work, even though it doesn't give me perfect results. I still want it to work, and that is exactly this damped least squares is doing. So this lambda is called the damp factor, right? So the damping factor or damp factor is this lambda, and it's a tuning parameter that you can pick. Then you might say, why is it the least squares method? What kind of cost function does it minimize? The cost function is this. It is the error in the joint velocities squared plus some gain, which is lambda squared, times the norm of the thetas, okay? The previous one that has 0 lambda, it will make this norm ideally to go to perfect 0. This one has a trade-off between minimizing this one and this one. So it tries to get this close to 0, but even if it doesn't go perfectly to 0, it is trying to force this norm of theta to get minimal. But none of them will be perfect because you're adding both of them. So the norm of theta will not be perfect minimum. The joint error will not be perfect 0. But it's a trade-off between the two. The closer you make the lambda, the closer this method gets to the pseudo-inverse. The bigger you make the lambda, the less accurate it becomes, but it typically is a little bit more stable, okay? So lambda is a regularization parameter, okay? Now, what happens in the solution? As lambda gets bigger, as I said, the norm of the final solution, the norm of theta, becomes a little bit smaller, but never perfectly the minimum. The error pose increases, and the number of iterations that you need to converge would increase. So you have to pay attention to how much of lambda you are picking. The good thing about it, as I said, this is stable near singularities, and it never gives you big joint velocity theta dots, so it makes the motion toward going from the initial position to the final desired position, makes it go smooth instead of random motions, if you remember in the Coppelia. The weakness, as I said, is less accurate. Lambda is not the absolute minimum, and you need to do some tuning for the lambda. Mathematically, if speaking, it replaces the inversion problem to, instead of just the sigma matrix becomes the sigma pseudo-inverse. This is what you get. You add this extra component to it, so your eigenvalues of sigma never become zero. They are always a little bit positive, so their inverse are never infinity, and it avoids explosion. Okay, so this is what we call the damped or regularized least squares method for inverse kinematics. And here is a summary. Pseudo-inverse is accurate. Damp one is moderate accurate. The pseudo-inverse is not as stable. This one is highly stable near singularities, more stable. The pseudo-inverse is fast. This is slower. And the parameter tuning, that doesn't really need anything. This one needs to select lambda. Now, let me tell you the last thing, which is practical guidance, and then I want to show you a MATLAB code here. So the important thing is this: which one of them do we pick? For that, you need to monitor your Jacobian or the Jacobian condition number, or if you want, you can measure that manipulability measure. And as soon as you see that the manipulability measure is indicating getting close to singularities, or the condition number is getting bigger, then you want to switch from the pseudo-inverse to the damped least squares method. What lambda do we pick? Typically, you choose anywhere between 0.01 to 1 for stability. Okay, so don't go more than 1. And don't make it super small, so have some trade-off. And you might have a hybrid strategy. That is exactly what I did in the Coppelia sim. First, I started with pseudo-inverse, and I had this as a backup. So in Coppelia sim, as I showed you, you can use sim-ik method pseudo-inverse for undamp and sim-ik method damped least squares for the DLS method. So here is a simple MATLAB code that I wrote, and all it does, it performs inverse kinematics on the 3DOF planar arm, where the only thing I want is x and y of the end effector. So clearly you have a redundant system here because you have 3DOF and all you want is 2 degrees in the workspace. The length of the links are these 3 numbers. Feel free to change them. My initial angles are basically 60, 45, and 30 degrees. The location I want to reach is when it's almost perfectly stretched with angles almost at 0. So y is 0 and x is some of these numbers, but slightly smaller. So it's almost very, very close to a singularity. Okay. If that number was not there, it was perfect on singularity. So I make it very close to it. And now I allow 1,000 iterations, a tolerance for the pose error of 10 to the negative 8. This is my gain that I multiply by delta theta for my iterative method. And I'm going to run the DLS method for 3 different values of lambda for you, 0.05, 0.2, and 0.08, all of them in that range I suggested. So here, first we check, make sure that initially whether you are in a singular position or not. Then we run this function, run PINV, and next we run the other one, which is for run DLS. So I run both of these, and then this is my kinematics. Okay, this is your forward kinematics, and this is the Jacobian that you need. Jacobian, of course, you need for basically pseudo-inverse of that, or just put it in the formula. And forward kinematics you need so you calculate the norm of the error. Okay, so this is your code, and it's just going to print results. It doesn't really plot anything. It's very simple. So let's look here. So initially, you see I started from a position that was not singular. If you look at the pseudo-inverse, it converged within 14 iterations. The final pose error is perfectly 0. And my magnitude of theta is about 6.36. Okay, now when I use the small lambda in DLS method, it needed more iterations, still could reach there because it's a small lambda, so it's close to PINV, it is doing a good job. And by the way, it's not like perfectly singular, but quite a bit close. And look at your theta. Your theta is not as minimal as this one is, okay, because you're adding some lambda. Now look, as I go down in the DLS method and lambda is increasing, look what happened to the theta. The magnitude of theta drops, as I said. The pose error gets bigger. You are getting less and less accurate. And these two with lambda of 0.2 and 0.8 could not even converge within 1,000 iterations. So they become much, much slower. Okay, so here you can clearly see the effect of lambda on the final theta, on the final pose error, and how many iterations it might need to converge, and compare it with pseudo-inverse. I'm going to share this MATLAB code with you under video description. Feel free to work with it and learn from it. And hopefully you could learn something new in this video. Thank you so much for your attention. I'll see you in the next lecture.